paging. Paging is a memory management scheme used by an operating system to manage virtual memory. Actually, the computer's memory divided into two types of memory segments. One is we called physical memory and another one is a logical memory. That logical memory is allotted by a computer system to a process. Physical memory address space actually in non-contiguous. Whenever there's been a memory space is available, an operating system allocating a space for a processor. That physical memory phase, fixed size of blocks, it divide. It is called frames. Actually, the computer kept all the information in a block. That block is called a frame. That was we call a original memory, physical memory. But in a virtual memory management scheme, or you can say as a logical memory, the logical memories blocks are splitted as a pages. So in paging concepts, both the physical memory and the logical memory, fixed size of blocks equally divided. The physical memory fixed size block called the frame, and then the virtual or logical memory fixed size of blocks are called the pages. The concept of paging is there the operating system link the virtual memories pages into physical memories frame. So how it will done that type of mapping, that type of memory management, that is the concept of paging. We can see that we are all having a keep track of all free frames. To run a program, n pages and we need to n free frame needed to load a program. That is the setup of page table. In page table, translate logical to physical address. Backing store likewise of split up. We already shown that in a physical memory there is a split up of frames. In a logical memory there is a split up of pages. So that type of management we do through this paging translation scheme. And page number, here we have a two partition, one is page number and page offset. In page number used as an index into a page table. Page offset table, that is page offset, combine the page address to define physical memory address. So for any given address space 2 power n, we have a page number and a page offset combination. The paging hardware diagram look like that. After the CPU, we have a P and a D value. The P represents the page table's value. In this page table, value also linked by a physical address space frame. So what we see there, logical address are blocked in the name of pages, that is block, it is separated as a blocks in the name of pages. Physical address with fixed size of blocks is here also available, it will be named as a frame. So through this page table, we link the logical address paging into physical address frame. That was the paging hardware diagram shown here. So we have a logical memory, page 0, page 1, page 2, page 3. You can understand easily in a logical memory when CPU allocate a memory address to a process, it continuously allocate a size value like page 0, page 1, page 2. But actually that is not be possible in physical memory because the operating system allocate whenever there is a space, then only it allocated. So you can easily refer in a physical memory in this example illustration. So the pages are allocated here and there, here and there. So for to resolving this issues, we have a page table. In this page table, you fixing that 0, 1, 2, 3 are representing the concerned page number. The concerned page number actually stored in the physical memory frame as 1, 3, 4, 7 like that. So the page table acts as a mapping in between logical memory and physical memory. So this was an example there. The whole n equal to 2 and m equal to 4. Totally, if we have a 32-byte memory or 4-byte of pages, we have that type of paging split up here. In a paging, calculating internal fragmentation, say for example, page size is 2.048 byte. Process IT is 72,766 bytes. We have a 35 pages plus 1088 bytes. Internal fragmentation of 2048 minus 1086, we got 968 bytes. Worst case fragmentation also 1 frame minus 1 byte, so that we can arranging a page like that. Solaris operating system support two page sizes. One is 8 KB and then 4 MB. Free frame for initial momentum, it all taken before an allocation, the free frames lists. From that, we can easily see that working of paging represented in a before allocation and after allocation. In the before allocation, we have the list of pages, page 0, 1, 2, 3, 4, and then we have a empty frame list. After that, we can assign through the new process page table from where we map pages to concern frame. So these are the important role of page table. The page table kept in main memory. The page table have a page table base register. We call as a BTPR to point to the page table. And then page table length register PTLR indicate the size of the page table. In this scheme, every data instruction access to memory access. One for the page table and one for the data. The memory access problem can be solved by the use of a special fast lookup hardware, which is called associate memory or translate lookup buffer, TLBs. Through these TLBs, it will be easily solved. We saw that how it will be the TLBs are what. TLB typically is small 64 to 1024 entries it have. So allocation of memory have a parallel sets like page number and frame. So in address translation, we have a combination of P and D. P is an associative register and frame out. So paging hardware, it shows on full-fledged paging hardware diagram. So after the CPU, we have a logical addressing as we discussed earlier. Here we fixing TLB for to solving the DCO. So page number and frame number parallelly matched here. So we have a TLB miss in the sense it will be presented in the page table. So through and frame and these offset value D, we can easily link a concerned pages location into physical memory. So when we deal with on effective access time, so associate lookup time unit we can be calculated. The hit ratio alpha value will be defined. The hit ratio is percentage of time that a page number is found in the associate registers. So ratio related to number of associated registers. So effective access time we get the formula of EAT equal to 1 plus that is on time unit alpha plus 2 plus the time unit into 1 minus alpha. So likewise we calculating the effective access time. We using on memory production here. Once we mapping pages to frame, we need to know whether the bits are valid or invalid. So valid invalid bit attached to each entry in the page table. The valid indicate that the associate based in the process logical address space, and thus a logical space is invalid, it indicated that the page is not in the process in a logical address space. So page table length register PLTPR we use it for that. Any violation result in a track of the kernel. So likewise we protecting through fixing valid or invalid bit in the memory protections. So the figure shows that when you are having the setup of pages, the page table having the value of B for valid and I for invalid. So we can also share these pages and shared pages used for sharing that information through multiple users. So we have a structure of page table there for sharing. Considerably to have a 32-bit base size 4 KB. From that we fixing on page table it have a different structure. So hierarchical page table, the breakup of logical address space into multiple bit is a simple technique. Two-level page table we use here. Two-level page table represented in that figure. So we can extracting that from page frame, outer page frame to page table, and then it will further accelerate as on a memory. Two-level page table as an instant a logical page number of 22 bits, and then we have an answer value 10 bit. So totally the logical address bit in 32 bits. So 1k bits, yes. Like that we fixing on two level base. Address translation schemes, for example, P1, P2 as in the pages, we have on a P1 as an outer page table, and then we have that definition page of page table likewise. So such 64-bit logical address base, we can also use 3-level page schemes. Hashed page table, we have a virtual page number in a hashed into a page table. This page table contains a chain of elementary hashed to the same locations. So likewise, if you have a match of found it, have a tested page table, especially useful for sparse address spaces, while memory references are non-contiguous and scattered. So the figure shows an example of an hashed page table. So one more we have on an invented page table. Rather than each process having a page table and keeping track of all possible logical address, track all physical pages, one entry for each real page of memory. Entry consists of virtual address of the page stored in the real memory location with information about the process that owns the page. So this is shown on invented page table architecture. We have a CPU, next to the CPU we have a PID and then P and T. So after that we are linked with a page table, then offset value link page into frame. Thank you.